definitions of orientation without the determinant. We will prove that the orthogonal group O of n has two connected components using a fibration. Extend this picture to the general linear group by polar decomposition. Define orientation without the determinant, and then prove that oriented volume is multilinear and alternating. First, the fibration. Define a map pi from O of n to the sphere S to the n-1 by sending a matrix A to its first column, which equals a times E1. The fiber over a unit vector V is all orthogonal matrices, whose first column is V. Over the base point E1, the fiber is precisely the block matrices with 1 in the top left and a matrix B in O of n-1 in the lower right. This shows the map is a fiber bundle with fiber O of n-1. Because the sphere is connected for n at least 2, the connected components of O of n correspond to the connected components of the fiber O of n-1. We do induction on n. For n equals 2, O of 2 has rotations, a circle, and reflections, a separate component. So it has two components. Therefore, O of n also has two components for all n at least 2. Now, the general linear group. By polar decomposition, every invertible matrix, A equals U times P, with U in O of n and P positive definite symmetric. The map from O times P to GL of n is a homeomorphism. The set of positive definite symmetric matrices is convex, hence connected. Therefore, the number of components of GL of n is the number of components of O of n times 1, which is 2. Using this, define orientation. A basis V 1 through Vn determines a matrix of columns. Its orientation is the connected component of GL of n containing that matrix. So there are exactly two orientations, the identity component and the other component. Swapping two vectors multiplies by a column swap matrix, which is a reflection in the orthogonal group, hence moves to the other component. So a swap flips orientation. Now, oriented volume. We define a function f on n vectors giving the oriented volume of the parallelepiped they span, normalized so that f of the standard basis equals 1. If we swap two vectors, orientation flips, so f changes sign. That is, f is alternating. If we scale one vector by a positive factor, a, the corresponding edge length scales by a, so volume scales by a. If we multiply by -1, a reflection flips orientation and flips the sign. Thus f is homogeneous in each slot. A shear adds a multiple of one vector to another. It preserves oriented volume. From shears we get additivity. F of u plus w equals F of u plus F of w in any slot. Together, homogeneity and additivity give linearity in each slot. Therefore, F is multilinear and alternating.